A presentation was put together in cooperation with Eugenia Buta, who unfortunately at the last minute couldn't make it. So we're going to discuss, basically, I'm not going to show you how to, do these things directly, but the idea is to familiarize yourself with key concepts in missing data and to make sure CIRA-affiliated researchers who have this problem, which is everyone, know what services we offer and what can be done, okay? And what should not be done, I might add, too. Oops. Okay, so what we're going to do is have a fairly brief description of modeling missing data using a Bayesian approach via WinBUGS software. How many of you here are familiar with WinBUGS? One, okay. And basically, we're going to focus, however, on multiple imputation methods available in R, in particular, the Amelia package, which incorporates some aspects of Bayesian modeling. Now, there's several elements that you need to familiar, and don't worry, I'm going to send everyone who attends the slides. I will send them to you so you can relax and you don't have to take notes. The key elements is the number of cases missing per variable, the number of variables missing per case, and the pattern of correlation among the variables. For example, I also, in addition to being here at CIRA, I also have an appointment up in internal medicine in occupational health where, for example, they have a data set just shy of 9 million people. And they were a bit upset because they were missing 60,000, had incomplete data. And I said, what? If you were working here in behavioral studies where, 100 people is considered good, you wouldn't worry. Now, the first thing that we need to be familiar with are the types of missing data. The sampling process involves both the selection of units and the process by which observations become missing, if you think about it. And for valid inference, we need to account why these things are missing, even if it is an educated guess. There are basically 3 categories of missingness. How many of you are familiar with these? Just Jamie? Okay. First is, whoops, I should have capitalized that, is missing completely at random. And that means that there's no difference between the characteristics of those observed and those missing. And this can be tested with something called Little's MCAR test, which I will go into in a little bit. Missingness is not related to the data values. Either the graduate student left part of the book on the train, or errors in lab results, entry mistakes, or subjects in longitudinal studies, subjects drop out of the study for reasons not related to the intervention, outcome, or other variables, okay? And that is sort of the gold standard. This is what we want, basically, hopefully, to detect. And the next is missing at random, which is actually a misnomer because it isn't really missing at random. It means that there's a difference, but it could be explained by other variables or data. Missingness depends only on observed data. For example, subjects are missing income in a study tend to be younger. You can deal with that on average than those reporting income. That can be dealt with. This is the disaster, missing not at random. And most of the literature calls it non-ignorable, understandably. And the difference cannot be explained. Missingness is directly related to the unobserved data. And the probability of reporting incomes, for example, depends on the level of income. In a clinical trial, the subjects drop out because they're too sick to come in for follow-up, and other problems. Here are the consequences. Most of you are aware you would have bias, and the estimates systematically deviate from the quantity of interest. No bias if it's MCAR, but bias can occur if it's either missing at random and missing not at random, okay? And especially the variance, it can change the standard errors, which of course is what anchors most statistical analysis. So you're in trouble there, and of course, wrong study conclusions, okay? And the impact of missing data depends on the amount of missing data and the mechanism of missingness, these three. The consequences of missing not at random means that you simply cannot remove the missingness and do the analysis, even if you seem to have a very large N number. In the case I cited above, if out of the 9 million, most of the 60,000 people who were missing and dropped out of the system, we were looking at industrial accidents, is because they had an industrial accident, then running the remaining data, however impressive the N number is going to give you false results. So not only the remaining data is biased in this case. For example, in a study I'm involved in with the University of Pennsylvania on early or late treatment, HIV treatment for infants in South Africa, we had to assure ourselves that the women who missed the second visit, that the child was alive, and actually had to have people in South Africa go and call or find before we could do anything else. Because if the children were very sick from their infection, or unfortunately had passed away, then we couldn't use, the remaining data would be biased in favor of those who were healthy. And very low, we couldn't draw a correct inference. And it's difficult to detect missing not at random because you might have the known unknowns. Do you know what I mean by that? In other words, you have to know what you don't know. Huh? As of all of his craziness, that's the one thing I have taken to heart, is that there are a lot of things you don't know, but frequently there are the unknown, the things that you don't know that you don't know. And that is what's going to trip us up. And distinguishing MAR from MNAR can be difficult, if not impossible sometimes. Okay? Let's take a look at Little's MCAR test. This was first written in 1988. The test is based on mean differences across groups of subjects with the same missing data pattern. And since the power of the test may be low, it is prudent to keep in mind that accepting the null hypothesis of MCAR, in other words, that there is no difference between the missingness and the observed, you still have to use your own judgment and prudence. It is not an instant cure. And, we can use it that way, but if you know for some reason that there is another reason for the missingness, then, Little's will not conjure that away. It's when you believe that it is at random and you have no other reason to think otherwise that you can apply this. Here at CIRA, we implement it in SAS, which usually is not my favorite program. I'm an R guy. But there's a neat code that I got from Dan Zelterman, and it runs beautifully. You can get a point-and-click version in SPSS for, I think the package is $4,000 or something. I'm a lot cheaper, yeah. So both Eugenia Buta and myself have run the SAS code successfully. Call on us. And this would be an example. If the p-value is not significant, then you don't have to, then you can consider the data missing completely and random and just proceed with it, okay? For example, in a paper I was a co-author on with Sheila Shenoy from Jerry Friedland's group, we had plenty of missing data in a South Africa study, and we conducted it on 4 individual factors to create what was called a laboratory clinical severity index, which is something that I worked with Sheila. And in these 4 tests determined that the missingness for hemoglobin, albumin, and alkaline phosphate were missing completely at random. Creatinine was not. However, in order to save N, basically, I created an index, a count of those, 4 laboratory things, which ones were abnormal in the wrong direction, and gave each individual a count of them. When we combine those, then voila, through the statistical sleight of hand, that instead of using the individual scores, using that, it became missing completely at random. And we were able to, get it through the reviewers, et cetera. Okay? And incidentally, that is actually, it is better to test everything at once. In other words, you put in, instead of doing each variable with the outcome variable, because of alpha inflation, every time you run a test at 5%, at p equals 0.05, the error rate is additive, actually, and keeps building up as you go. So it's better to put everything together and test it. And these were the scores. But this was the all 4 count. It's this is a very specific example, but I just wanted to use it since it's published. Jamie, you look confused.
No, I think it's sad because I think you tell another story that your creatinine is significant, the other one's not. So what you're doing, statistically, right? You're combining what's significant, what's not significant. I realize the little test does kind of I don't know. To me, it just seems a little bit medically disturbing that you're creating an index of non-significant values, and then you have a significant value that you're just kind of filtering in there. And
no, that's an adequate. Well, no one's ignoring the thing. It's just to see, these are all, as these are all indicators of organ failure, and to see if, and it turns out of all the tests, these 4 are the key, that, if you don't have, bad lab readings for these 4, you were more likely to survive the extensively resistant, TB and HIV co-infection. Okay, but yeah, that's valid. But what's the alternative? Just not publishing anything? Okay. Okay. Now these are a list of horrors that you should not do. Complete case analysis. Without doing anything else, just throw out the missing and run your data. And as we've seen, this can lead to a lot of problems. Earlier, single imputation. In other words, just do a linear regression on the known values, and then pick the values from the regression line. Does everyone follow me on that? Yeah. Pick the values on the regression line and fill them in. And what would be the problem with that right off the bat? Can anyone take a guess? Okay, well, if you are picking the regression line, then you're basically suppressing the variation and decreasing the variance. So it's they also, so obviously, you're asking for trouble there. Missing data indicator, missing category, and you can do that, but also, it obviously can lead to bias. And then last observation carried forward. And this was done, especially in the 60s and 70s. I know those of you in clinical medicine will probably go, oh my God, did they really do this? They did. In other words, here are the values. And, well, that one was a 24. And again, you're suppressing variation pretty seriously and all but defeating the purpose of a longitudinal study if you do too much of this. Okay, so there was a really good paper, and I will send you all the references too, Little, of Little's test, talked about Bayesian algorithms, which are model-based in contrast to these older imputation methods. So we already went over this. There were things like hot deck and so forth and so on, which you don't do. But a model for data is defined, and then it results in the likelihood or posterior distribution of the model. And the estimates in general, including those of the variances, can be formed to account for the missing data. And this, before multiple imputation came into its own within the last couple of years, was a very good alternative to missing data. And it was done in something, how many of you know what WinBUGS is? No? Okay. It was a joint endeavor between the MRC Biostatistics Unit at Cambridge and the Department of Epidemiology and Public Health of Imperial College London. And it stands for Bayesian, forget the I, inference using Gibbs sampling. And WinBUGS just means it runs in Windows. Originally, was designed for Linux-based systems. And how many of you use Ubuntu by any chance? No? No Linux-based? Oh, Lord, yeah. All this freeware, all this stuff that's available, no viruses, no, rootkits. Oh, well. Okay. But at any rate, WinBUGS runs perfectly well in Windows. It can handle analysis for complex statistical models, missing data, measurement error. An important point is there's no closed form for the posterior distribution, and the Bayesian posterior inference is achieved through a Markov chain Monte Carlo integration. Okay? How many of you are familiar with what a Markov chain is? Let me just take a second. A Markov chain means that only the immediate previous observation informs the current one. For example, an example I use is someone goes to a bar, starts drinking, and starts doing 90 miles per hour and runs the car into a tree. Okay, the previous state that he was doing 90 miles per hour is informative of the outcome. The fact that he was doing 30 miles per hour before that and that the car was parked before that are irrelevant. So just to give you an idea, however, WinBUGS is not for the faint of heart. This is an example using non-informative priors with what's called the half-normal distributions with 50,000 iterations and a burn-in of 4,000. In other words, you actually are going to work with 46,000. And that's page 1. And that's page 2. No, this is in WinBUGS. And there's a bugs to R. So let's go. Most of you who are casually dealing with missing data are not going to sit down and learn WinBUGS. And really, you don't have to. One, you could ask me if you thought that was the best way to go, and I would do all this. Or Eugenia, who got her PhD in Bayesian analysis. But generally, we are recommending multiple imputation if you can satisfy the MCAR or MAR conditions. You know, and actually in Bayesian analysis will not help you if you are missing not at random. You're just kind of, you know, apply for more grant funds or something. Okay, this time we're going to perform imputations of the missing data m times, usually 5. And then the data sets are analyzed separately and the results across the analysis are combined, and I'll get into that. And this would be an example of multiple imputation where you had missingness, and it would fill in 5 different data sets, so to speak. So in Plan B, since you looked at the WinBUGS instructions and threw your hands up, would be to use the Amelia package in R. And it is indeed named for Amelia Earhart, rather whimsically, as a symbol of missingness. I don't know, I always thought that's a bit dark, but what, do all of you know what R is? Yes? Yes? Okay, well, briefly, it's both a program and a software package. It's derived from the S programming language created by John Chambers, who is not the same John Chambers that, what do you call it, the chairman of the board, who's, you know, the very prominent Republican donor. It's not him. At any rate, the current version was developed in New Zealand by Ihata and gentlemen. And it's freeware and open source. There's no charge, and the underlying code is available to anybody. And that's why there's so much in it. And it has become the de facto gold standard. It's considered the most publishable, most consistent. And along with the standard software, there are almost 3,000 specialized task-specific add-on packages, latent class analysis, survival analysis, you know, just anything you can think of. There's a package you can add on. And I would like to add that, you know, as freeware with multiple people across different countries and cultures, there's a wonderful absence of jargon and program-specific language. The instructions are in English. The error messages in the, when, you know, if you make a goof, it says there's an error on line 5. You know, that's it. It doesn't say code 555, you know, and all this other nonsense. The version we're going to use is the package developed by Honecker, King, and Blackwell, and it was just revised and updated on April 3rd. So this is as up-to-date as you're going to get, folks. Okay, what exactly does Amelia do? It resamples the original data set using a bootstrap algorithm. It implements an expectation maximization algorithm. And an expectation maximization algorithm is an iterative method of finding the maximum likelihood or the maximum a posteriori estimates of parameters in statistical models. Okay? And don't worry, I will send you these slides. You can look up the terms in depth. And it uses all of the data to estimate the missing values. If you think about it, a sample, even a large one, even with a large amount of missingness, is basically one realization of the data. You know, a sort of possible reality, if you think about it. And Amelia creates other realizations of the data using the aforementioned algorithms. You know, what we see when we sample is just one possibility, really. And these, Amelia, the default is set to 5. So, you know, that usually is enough realities for most people. So all 5 are combined to apply standard statistical analysis and further reduce bias. And this is done within Amelia. They use Zelig, which is every man's statistical package to do this. Also, you know, named after the Woody Allen movie. But at any rate, That's how it works. So as we've said, it can multiply missing data in a single cross-section, such as a survey, from time series like variables collected for each year in a country, or from a time series cross-sectional data, such as collected by years for each of several countries. As I've said, it implements a bootstrapping algorithm that gives essentially the same answers as the standard approach, but it's faster and can handle many more variables. And it's basically faster than the PROC-MI in SAS, for those of you who've fought with that thing. And it basically generalizes the existing approaches by allowing for trends in time series across observations within a cross-sectional unit, as well as priors that allow experts to incorporate beliefs they have about the values of the missing data in their cell. Okay? And there's a GUI with it. So all of this, once you set it up, can be point and click. You know, it'll look just like a simple SPSS package or something. You just say, impute this. And it will map the missingness for you. And here is the code compared to the WinBUGS. You know, this is the, you've had to set the number of imputations you want, or just set, this will give you 5, which is what everyone uses, what's published. That's the data set. Bam, done. It's not perfect. And I thought in all fairness, I should show you one of my mishaps here. Here is the observed data, okay, in black. And here were the mean imputations. So in fact, I did have to go back and tweak it a little bit. But it gives you these sort of graphs to see whether or not you're off, completely, off in doing this. Okay, so as I said, the purpose today basically was to let you all know what we can do for you, okay? For any SIRA-affiliated research, we can do a Little's test for you, okay? Just send us the data and the variables that you want us to see, and obviously the outcome and hopefully the explanatory variables or what have you. We can do the Bayesian simulations. We can explore the missingness using, I didn't go over this, but we can also do t-tests and things like that to see how different the people who are missing are from those who have complete data. And for anyone who wants it, I can sit down and either do the multiple imputation for you or take about 15 to 20 minutes and teach you how to do it in R. Like I said, because it has its own GUI, you don't even have to know R. There's no big coding. There's that one line and then a few other adjustments if the mapping or the graphing of the imputation, as I showed you, doesn't look so great. Okay, well, thank you for your attention.